In our previous tutorials on rheology, we discussed a lot of whats. What are the essential elements of rheology? What deformation forces are materials likely to experience? And what do the flow profiles of various fluids look like? In this video, part 4, we're going to examine how do rheological agents work the way they do to deliver rheology? And for that, we need to explore chemistry. Yeah, chemistry. All rheological agents can be classified based on how they function. They can either be non-associative or swelling types, or associative, the adsorptive types. The swelling types can work in either clear formulations or formulations that contain components, such as pigments, extenders, or matting agents. These swelling types affect the viscosity of the system's medium, such as the organic solvent or the water phase of a formulation. In contrast, the adsorptive types requires a formula's components, pigments, extenders, or matting agents, to absorb onto and thus form a network, or what I like to call controlled agglomeration. Examples of swelling rheological agents include castor oil-based derivatives, silicas, and polyamides. And there are others, including organoclays, alkali swellable emulsions, and cellulosics. These non-associative types offer the appearance of swelling as they form a three-dimensional network with themselves and expand or swell by enclosing the formula's medium, solvent or water, within that network. The swelling mechanism works independently and can function in either clear systems or in formulations that contain other components. The associative types of rheological agents include oxidized polyolefins and hydrophobically modified ethoxylated urethanes, or URs. And there are many other types, like HAZE, hydrophobically modified alkali swellable emulsions, and URAs, hydrophobically modified ethoxylated urethanes with an alkali swellable emulsion component. Again, these products adsorb onto the surface of formulating components to form a network structure. And as you recall from a previous tutorial, a key requisite for rheology is morphology, and a network structure contributes to morphology. Let's first look at castor oil derivatives to understand how they create this network, this morphology, and thus rheology. Castor oil, like all vegetable oils, are triglycerides. A triglyceride is a triester of glycerol and 3 fatty acids. In this particular triglyceride, we show 3 different fatty acids: stearic acid, which is fully saturated; oleic acid, which has 1 site of unsaturation or 1 double bond; and linoleic acid, which has 2 sites of unsaturation or 2 double bonds. The predominant fatty acid in castor oil, however, is ricinoleic, an 18-carbon acid with 1 double bond and a pendant hydroxyl group. If we hydrogenate this oil, we eliminate the double bonds and we're left with 12-hydroxy stearic acid as the predominant fatty acid. Therefore, when we talk about castor oil derivatives as rheology modifiers, we're talking about hydrogenated castor oil. And it's the pendant hydroxyl groups bound to the ricinoleic acid that leads to hydrogen bonding, which in turn plays a major role in setting up a network structure. Let me show an example of hydrogen bonding between 2 carbon chains that contain hydroxyl groups. The electrostatic attraction of these molecules to each other develops a weak network which can be easily shattered with shear, yet can rebuild again when the shear is reduced or eliminated. Let's now examine how hydrogen bonding accomplishes just that. Recall that an atom contains a nucleus with both protons and neutrons, as well as orbiting electrons at various energy levels or electronic shells. The number of electrons equals the number of protons in an uncharged or electrically neutral atom. The number is also the atom's atomic number. The innermost shell has a maximum of 2 electrons, and the next 2 electron shells can each have a maximum of 8 electrons. This is known as the octet rule, which states that, with the exception of the innermost shell, atoms are most stable when they have 8 electrons in their outermost shell, or what we call the valence shell. Now, the element hydrogen, with an atomic number of 1, has only 1 electron orbiting its nucleus. It would prefer to complete its shell with a second electron and become more stable. One way to achieve that is to share its electron with another hydrogen atom and thus have both electrons orbiting around the 2 nuclei. So a pure covalent bond is established where the electrons are shared equally between the 2 atoms. Now, oxygen, with an atomic number of 8, has 8 orbiting electrons distributed over 2 energy level shells. Shell 1 is already complete with 2 electrons, but shell 2, its valence shell, has only 6 electrons. It needs 2 more to complete its shell and become stable. So how do we accomplish that? Now, before we get into that, let me first explain an atom's electronegativity, which is the atom's propensity to attract electrons towards itself. And the higher the electronegativity, the stronger the attraction. Hydrogen has an electronegativity of 2.2. Recall that when we place 2 hydrogen atoms next to each other, they equally shared a total of 2 electrons. Of course they would. Each atom is the same with the same electronegativity. One has no more influence over the other in terms of attracting electrons. Oxygen, on the other hand, has a higher electronegativity of 3.44. Of course it would be higher since its outer shell has 6 electrons, needs 2 more to complete its shell, and therefore is 3/4 of the way there. So its desire to pull electrons towards itself is greater than hydrogen with its 1 electron. As a result of oxygen taking more than its fair share of electron density, it becomes slightly negative. And at the same time, the hydrogen atom, now having less than its fair share of electron density, becomes slightly positive. This is described as a polar bond. So now let's return to the hydrogenated castor oil molecule. This is one possible configuration of the triester, where the 3 fatty acids are lined up to one side, or alternatively, it can orient like this. Let's highlight the ester groups as well as the hydroxyl groups with their respective electrostatic charge. Now let's view the resulting attraction between the hydroxyl groups as a result of hydrogen bonding. In this configuration, we have a hydroxyl group on one end of the molecule, ester groups in the middle, and hydroxyl groups on the other end. The molecules congregate with each other to form needle-like structures, which in turn forms a network and develops morphology, a requisite for rheology. Here is a ball and stick representation of the molecules. Notice when these molecules form a network due to hydrogen bonding, we have pockets or voids for pigments, extenders, or other formulation components to nest or be suspended in. And if we were to apply shear, the hydrogen bonding will be temporarily broken, the network collapses, and viscosity is reduced.